This presentation will review the Stanford HIV Drug Resistance Database Drug Resistance Interpretation Program. The first few slides will provide basic background information, while most of the presentation will review how the program is used. These are my disclosures. Genotypic HIV drug resistance testing is performed for three main purposes. In upper-income countries, it is performed to optimize the management of individual patients. In lower and middle-income countries, it is performed largely for the surveillance of transmitted and acquired HIV drug resistance. It is also used as part of the inclusion criteria for participants in a clinical trial and as an outcome variable in clinical trials. For the second and third goals, it is important to use a consistent approach so that the results of different studies can be compared with one another and can be combined. For the first goal, genotypic resistance test interpretation requires that the results of testing are integrated with additional clinical data, such as a patient's past treatment history, previous genotypic resistance test results, and plasma HIV-1 RNA levels. Knowledge of published HIV treatment guidelines is also required in order to use the results of genotypic resistance tests to put together an antiretroviral treatment regimen. The HIVDB interpretation system comprises numerical penalties for individual drug resistance mutations, as well as additional penalties when certain combinations of drug resistance mutations occur. The individual plus combination drug resistance mutation penalties for a specific antiretroviral drug are added together to derive a total penalty score for that drug. Each drug resistance mutation is also accompanied by a comment that provides additional information about it. A rules-based interpretation system seems somewhat archaic in this era of machine learning and AI. However, for reasons that go beyond the scope of this talk, we don't believe that it is currently possible to develop an optimal machine learning algorithm for genotypic HIV drug resistance interpretation. Individual drug resistance mutations receive penalties that range from 5 to 60. The penalties are titrated so that when the penalties for a drug are added together, they generally fall in a range from 0 to more than 100. This table indicates how the numerical score is translated into one of 5 different resistance levels, from susceptible to high-level resistance. A few drug resistance mutations have negative scores for certain drugs. These hypersusceptibility mutations can mitigate the effect of other drug resistance mutations on that drug. The table also indicates what is meant by the different levels of resistance. Susceptible is assigned when a virus displays no evidence of reduced susceptibility compared with a wild-type virus. Potential low-level resistance is assigned when a virus has drug resistance mutations consistent with previous antiretroviral exposure or contains drug resistance mutations associated with resistance only when they occur with other drug resistance mutations. Low-level resistance is assigned when a virus has drug resistance mutations associated with some degree of reduced in vitro susceptibility or a suboptimal virological response to antiretroviral treatment compared with a wild-type virus. Intermediate resistance is assigned when there is a high likelihood that an antiretroviral drug's activity would be reduced, but that the antiretroviral would still retain significant antiviral activity. Finally, high-level resistance is assigned when a virus has drug resistance mutations predicted to confer a level of resistance similar to that observed in viruses with the highest levels of reduced in vitro susceptibility for that drug, or in viruses that have little or no virological response to treatment with the relevant antiretroviral. The drug resistance mutation penalty scores and comments are created and updated based on three main types of data or considerations. Are the mutations selected by the drug? Do the mutations reduce drug susceptibility? Or do the mutations reduce the virological response to a regimen containing the drug? With respect to selective drug pressure, three types of data are considered. First is the mutation of polymorphism that occurs naturally in the absence of selective drug pressure. Empirically, such mutations have been very rarely associated with reduced drug susceptibility because the most commonly used inhibitors target proteins that are highly conserved. Second, mutations that are selected in vitro by a drug are often, but not always, highly predictive of the main mutations that arise in patients experiencing virological failure while receiving the drug. Drug susceptibility data associated with a mutation or combination of mutations can be performed on site-directed mutants. In this scenario, it is possible to strongly link the effects of individual mutations or combinations of mutations to reduce drug susceptibility. However, most drug resistance mutations and combinations of drug resistance mutations have not been studied in this way. Indeed, most of the virological susceptibility data comes from clinical isolates. These data are complex because clinical isolates often contain many different combinations of drug resistance mutations. Finally, the virological response to a regimen containing the drug of interest is theoretically the most important type of data. There have been several highly informative clinical trials that have demonstrated associations between specific pre-therapy drug resistance mutations and the risk of virological failure. However, many retrospective studies have had too few patients relative to the large number of covariates associated with response to therapy. For example, the patient's complete art history, plasma virus load, the drugs used in combination with the drug of interest, and the level of adherence to therapy. Moreover, most retrospective studies have been confounded by the fact that the results of genotypic resistance testing were used to guide the choice of therapy. This slide shows how to access the HIVDB drug resistance interpretation program from the Stanford HIV drug resistance database homepage. The sequence interpretation program accepts either lists of mutations, one or more FASTA sequences, or an NGS FASTQ file. FASTA sequences usually represent Sanger sequences or the consensus of the many reads obtained from next-generation sequences. This slide shows how lists of mutations are analyzed. I've highlighted several additional parts of the page, including a link to the release notes and the drug display options. By default, the program shows only those antiretrovirals that are still being used commonly. Most often, users type in RT, protease, and integrase mutations in the three text boxes. However, it is also possible to use drop-down menus to select each of the drug resistance mutations. The text boxes allow the mutations to be entered in a variety of different formats. By default, the mutations are entered and saved until the reset button is clicked, enabling the user to return to the page and modify the mutation list even after the interpretation is obtained. This slide shows how to either paste in or upload a set of FASTA sequences. At least 1,000 complete PAL sequences can be pasted in. There are two main output options: HTML or machine-readable file, usually a CSV file. Among the machine-readable formats, the most useful are the sequence summary and the resistance summary. The HTML output is fine if a small number of sequences is entered, but machine-readable CSV files are much more useful if many sequences are entered. This slide and the next one will review the HTML output of the interpretation program. This is the only way to review the results when a mutation list is entered. It is also a common way to review the results when a small number of sequences are entered. The very top part of the results show the region that was sequenced, the closest matching reference sequence, and its genetic distance from the submitted sequence, and a link to the nucleotide alignment. This example shows that the sequence contained the complete integrase gene, and by clicking on the plus sign near the subtype, one can see the top 10 closest matching reference sequences. The second part of the output contains a figure showing the mutations defined as amino acid differences from the consensus subtype B reference sequence. Drug resistance mutations and mutations that likely reflect sequence quality control issues are indicated each in a different color. Here I'm showing two drug resistance mutations. Beneath the figure, there is a textual summary of sequence quality issues when they are present in a sequence. These include stop codons, frame shifts, mutations suggesting that ApoBec-mediated G to A hypermutation is present, and highly unusual mutations. The remainder of the output includes the drug resistance interpretation for each gene that was sequenced. For integrase, protease, and capsid, the mutations are divided into major, accessory, and other categories. Other indicates mutations that do not receive penalty scores. For RT, the mutations are divided into NRTI, NNRTI, and other categories. The next part of the output contains the drug resistance interpretation based on the 5 levels shown previously. This is followed by the list of mutation comments. The final part of the output for each gene contains the mutation scoring table, which shows how the individual and combination drug resistance mutation penalties are added up to yield the total score that is used to assign one of the 5 drug resistance levels. If a large number of sequences are entered, then it makes more sense to select one of the spreadsheet output options, of which the two most common are the sequence summary and resistance summary files. This figure summarizes the output of the sequence summary file. Overall, the file contains 1 row for each sequence and about 40 columns. The first column contains the unique sequence ID, and the next 7 columns indicate which genes were sequenced and the range of positions that were sequenced for each gene. There is a column with the genetic distance to the closest matching subtype, and a column indicating the proportion of positions containing a mixture of more than one nucleotide. In newly diagnosed untreated persons, the proportion of positions with mixtures has been shown to correlate with the duration of infection. The next 9 columns indicate the 3 categories of mutations for protease RT and integrase. The next 4 columns list the drug resistance mutations that have been used for surveillance of transmitted resistance. The surveillance drug resistance mutations, or SDRMs, overlap a lot with the drug resistance mutations shown in the preceding columns. However, the SDRMs differ in that none are polymorphic and that none are extremely rare. The treatment-selected mutations, or TSMs, are non-polymorphic mutations that have been shown to be significantly more common in treated persons than untreated persons. These include some very rare mutations that have not been well studied and that therefore do not have mutation penalty scores. They generally only occur in combination with other well-established drug resistance mutations. There are 12 columns highlighting QC issues, and the last column is a URL containing each of the amino acid mutations, which allows the HTML output to be viewed in the future. This slide summarizes the columns shown in the resistance summary spreadsheet. In addition to having the 9 columns showing each of the protease RT and integrase mutations, it also has columns showing the total score and the resistance level for each antiretroviral drug. This and the next 2 slides will summarize how NGS reads are analyzed, which begins by clicking on the Input Sequence Reads tab. This requires 2 steps. The first requires converting 1 or more FASTQ files to a format we developed called a codon frequency or CodeFreq file. The following slide will describe codon frequency files in detail. This conversion can take place by dragging the NGS FASTQ files to the box at the right or by uploading 1 or more FASTQ files. If 2 files have the same prefix, they are considered to be paired files. The conversion of a FASTQ file to a CodeFreq file takes about 2 to 5 minutes, depending on the size of the file. This conversion can be done on our website or on the user's computer using code that we have written. Generating a report from the CodeFreq file takes about 2 to 3 seconds. The user can also select the minimum number of reads required for a region to be considered to have adequate sequence coverage, the mutation detection threshold, which is the minimum proportion of reads containing the mutation for it to be considered to be valid, and the maximum allowable proportion of mixed nucleotides. By default, the minimum number of reads is set at 50, and the mutation detection threshold is set at 10%. CodeFreq files contain tables with 7 columns in which the frequency of each codon at each position is indicated. In this example, the different codons present at RT positions 200 and 201 are shown. Overall, there are approximately 34,000 reads encompassing these 2 positions. Most of the codons are present at very low levels and likely represent PCR or sequencing machine errors. The mutation T200A is present in about 21% of reads. Nearly all of the remaining mutations, with the possible exception of the silent mutation present in 2% of reads at position 201, likely represent background noise. There are 3 main advantages of working with codon frequency files. First, they are much smaller than FASTQ files. Second, drug resistance interpretations can be generated very rapidly because the time-consuming part of the analysis has gone into the creation of the codon frequency files. Third, the distribution and the frequency of non-consensus codons provides an important measure of quality control. For example, if the level of background noise is high, it is important to be conservative when setting the mutation detection threshold. Otherwise, many of the detected variants will be sequence artifacts. The one disadvantage of codon frequency files is that it is not possible to know whether subconsensus mutations at different positions occur on the same reads. However, this is a minor disadvantage because it is never possible to be sure that mutations are linked on the same viral genome unless single genome amplification is performed prior to sequencing, and because linkages between mutations is not considered during drug resistance interpretation. Code-free files have two advantages over the established variant call format or VSF or VCF files. They are interpretable without a reference sequence, and they can be used independently from an accompanying SAM or BAM file. This slide shows those aspects of the output that are unique to the analysis of NGS files. The median read depth is shown, and those parts of the sequence that have fewer reads than the minimum read depth are also indicated, although I'm not showing those warnings on this slide. After the interpretation is obtained, it is possible to reset the minimum read depth and to adjust two different thresholds: the proportion of positions allowed to contain a mixture of nucleotides and the mutation detection threshold above which a mutation has to be present in order for it to be considered valid. Changes to these three parameters will be immediately reflected in the consensus sequence, in that a lower mutation detection threshold will result in more nucleotide ambiguities and the detection of more low abundance mutations. The list of reported mutations may change, and if they include drug resistance mutations, the overall report will change. At any time, the final consensus sequence can be downloaded in FASTA format. The output also indicates the read coverage at each position and the proportion of reads for each mutation. Finally, this part of the output can be used to help select a sound mutation detection threshold. This slide shows an overall schematic of the drug resistance interpretation programs on our website. Users can submit a list of mutations, one or more FASTA sequences, and one or more code-freak files. Code-freak files can be generated from FASTQ files on our website. The process can be automated using open source code. The code is available as a Docker image so that it can be run locally also on the user's computer. All of the output is delivered to the user using a GraphQL web service, which we use to generate the output on our website in a variety of different formats. However, if users want to control the process of interacting with the drug resistance interpretation program and of formatting the output, they can access the GraphQL web service through its API. They can write their own client or use a client we developed called Sierra Pi. They can also run the entire program locally using the Sierra Docker image. Thank you for your attention, and if you have questions, don't hesitate to email us at the email shown on this slide.